Alright, today we're going to be looking at series and parallel circuits. We're first going to look at a series circuit, go through the calculations that are required to solve for this. There are 5 things that we're going to solve for today. What's one of the 5 things that we're going to solve for? Okay, so the total current. What else? Jimmy?
Voltage drop across each resistor.
Good. So we have voltage drops across each resistor. So we have 1, 2, and 3. So we can call this R1, R2, and R3. Another item? Total resistance. Good. So these are the 5 things that we want to solve for today, and then we're going to prove Kerckhoff's voltage law, which we haven't really talked about. We kind of skipped over that slide, but we'll discuss that, what that is, once we solve for these 5 things. Okay? Which one of those is the easiest to solve for? Well, to find current, what do you need? What 2 values? You need voltage and resistance. Do we know the total resistance? No. So we can't solve for total current yet, so we should probably start with the total resistance. Okay? So, I'm going to start that over here. What's our equation for total resistance in series? Yeah, and this should make sense. Because if you're in a little electron and you're going through this circuit, you have to pass through each of these resistors in a row. So it's like going through the sum of all of them. I've got to go through this one and this one and this one to get back. So it's the sum of the 3 resistors. So again, if we look at our rules for addition with significant digits, we're going to take a look at that today as well. How many significant digits does 180 have?
2.
Now, when we add, what are we looking for? What's our rule for addition? The least precise. So we look at place values that are significant. So this one here, this 8 is our least, like this 0 is not significant. So the 8 is our last digit that we have that's significant. And that 8 is in what position? It's in the tens. 2 is in the, and the 7 is in the. So then our answer is good to the tens digit when I add them. So you should have your calculators out. You can calculate along. So again, all I'm doing is I'm just plugging it in. 180 plus 220 plus 470. Again, good to the tens digit. So I put 870. I prefer if you box in your answers or circle them, or you can use a cloud if you want to. You know, a cloud. So.
Yes.
Hey, if that floats your boat, then. Alright. So now that we know the total resistance, what is this telling us? Here's what it's telling us. It's essentially saying this circuit can be simplified. To this. It's saying essentially we have a circuit with a battery and a single resistor that's 870 ohms. This is an equivalent circuit to this. Does that make sense? Now, if I know the voltage and the resistance in the circuit, what can I determine from those 2 quantities? I can find the current that's being drawn from our source, which we call the total current. So that's what I'm going to solve for next. The total current is the voltage divided by the total resistance. Voltage is 9.0 volts, and our total resistance is 870.0 ohms. What did I do there? This number has 2 significant digits. Because it was a calculated value, I'm using a calculated value in a calculation. I'm carrying extra digits and underlining. They just so happen to be zeros. That's fine. A lot of times they won't be zeros. Do this in my calculator. Take 9 divided by 870. I get this value in my calculator. I'm going to go ahead and write it down. What is the unit that should I get out of volts divided by ohms? I should get amps. Now, when I divide, what am I looking for? I'm looking for least number of significant digits. So 9.0 has 2, 870 has, no, these are underlined so they don't count, so it has 2. So my answer should have 2, correct? Are these zeros significant? No, it's these 2 right here, and then I'm going to underline the rest. Now, do I want to write my answer as 0.010 amps? No, we want to write it because we are going to be engineers in engineering notation. What would we have to do then? Move the decimal which way? To the right by groups of 3. So if I move it one group of 3, am I in between a number between 1 and 1,000? Yes, what's that number? Not 10. 10 point. Okay, but we're going to round that off, right? Because we have 2 significant digits, so 10 point does it. What's my prefix? Good. Again, this number is smaller than this, so I need to use a small exponent. Box in your answer. That's what I'm looking for there. If you need to show an extra step in here and show that this is 10 times 10 to the negative third amps before you move to that, that's fine. Okay, if you can do it straight from here to there, perfect. Questions on that? If I know the total current leaving the battery, how much current goes through this resistor? The same? Same? Same. There's only one path for it to go. So all the current leaving the battery has to go through each of these. So if I know the current through this resistor and its resistance, what can I determine? So guess what I'm going to do for V1, V2, and V3? That same thing. What's my equation to solve for voltage? Good. Current times resistance. What am I using for my current value? Well, I want it to be in amps, so I'm actually going to use this value up here with those extra digits because I want to eliminate round-off error. So I'm going to use this value right here, which is 0.01035 amps. Again, you could put 345, that's fine, but as long as you're keeping 2 extra digits, I think that's appropriate. I use parentheses to kind of group my items here. My resistance is 180 ohms. How many significant digits should I have in my answer? 2. Answer has 2. So again, I just multiply. Actually, technically, this number is a 4 right there. Here's the number in my calculator. Everybody see why it's a 4? Because the 4 is after it. This became a 5, and then this became a 5 earlier. That's called a double round. So I rounded this number, then I reused this number to round again. That's a double round error. You don't want to do that. You want to look directly after it. It is a 4. Again, it's not going to make a huge deal on that stuff, but just watch so you don't double round on a final answer. That's kind of key. Multiply these two together. So I got this number here times 180. I get this value. Again, how many digits are good? 2. I'm going to keep extras and underline them just for future reference, so I'm going to use 1.862. Unit. Volts. So I round this to 1.9 volts. Okay, do V2 and V3 on your own. Again, you can pause the video, come back, and see how you did. Okay, so here's V2. Again, I took current times resistance to get the voltage of 2.3 volts. And then V3, again, current times the resistance of the third resistor to get 4.9 volts. Here's what you should notice. What do you notice about resistance and voltage values? As resistance increases, what's required to keep the current moving through it? More voltage to push it through, right? So that's what we should notice in our values, that the higher resistance that an item has, the more push or voltage across that resistor there needs to be. Now, let's look at Kerckhoff's voltage law. This is for series circuits only. But what his law states is that the total voltage from the source is equal to the sum of the individual voltage drops on the resistors, or the components that make up that circuit. So what is my total voltage that's applied on the circuit? 9 volts, right? So it should be the sum of these three. So if I use extra digits, that's why I kept them up above, is to prove this. So if I take those three values and add them up, just confirming that this is true, I have 1.862 plus 2.275 plus 4.860, and I get this value in my calculator. And again, using addition rule, this number is good to the 10th, 10th, and 10th, so my answer is good to the 10th. So what does this number round to? It checks out. Happy calculating.